Buenos días, soy Miriam Peña del Instituto de Astronomía de la UNAM y en primer lugar quiero agradecer a los organizadores de Friends of Friends 2021 haberme invitado a participar en esta conferencia. Voy a mostrarles mi presentación ahora. So there it is. There it is, I expect you can see it properly. I'm going to talk about planetary nebulae as clues for stellar nucleosynthesis and the evolution of abundance gradients in these galaxies. Planetary nebulae are ionized envelopes around an evolved star. Great efforts have been devoted to detect and analyze planetary nebulae in the Milky Way and nearby galaxies. Galaxies of the local group and beyond have been surveyed with the largest telescopes available, searching for fainter and farther planetary nebulae. And why so? Why planetary nebulae are important? Because they are good tracers of their parent population, which are low intermediate mass stars in the transition from red giant to white dwarf. The chemistry, initial final mass relation, binarity of limbs can be analyzed through planetary nebulae. They allow a chemical study and evolution of the parent galaxy, as planetary nebulae are indicators of the metallicity of the interstellar medium at the formation time a few gigayears ago. Also, planetary nebulae are useful to analyze the galactic kinematic and can be used for distance determination and for cosmology too. In external galaxies, planetary nebulae appear stellar. In Andromeda, more than 700 planetary nebulae have been detected. A particular section is shown here. To the left, in blue crosses are the planetary nebulae. To the right, in red, the H2 regions are shown. And please notice that H2 regions delineate the spiral arms, while planetary nebulae are more widely distributed. Here is a typical spectrum of a planetary nebula: a faint continuum and very intense emission lines. Planetary nebulae are the most luminous phases of evolution of their central stars, with luminosities of about 10 to the 4 solar luminosities, and much of its emission comes out in a few bright narrow lines. The most intense lines are oxygen 3, 4, 5007, and 4969, also H beta, H gamma, and others. Oxygen 3, 5007 can emit as mass as 10 to the 3 solar luminosities. So planetary nebulae can be detected at very large distances beyond the Virgo cluster. The analysis and the spectrum. The analysis of the spectrum provides the physical conditions and the chemical abundance of many elements. What about the central stars of planetary nebulae? Stellar abundances and other characteristics should be determined directly by modeling the stellar lines with the code to be compared with the planetary nebulae chemistry and to provide details of chemical evolution and nuclear physics in limbs, like convection, mass loss, rotation, mixing length theory, efficiency of the third rejab, and others. However, these stars are faint, with absolute magnitudes of about -4, which means apparent magnitude of about 18 in the Large Magellanic Cloud and 23 in M31. And they are embedded in a bright nebula. Therefore, it is very difficult to determine stellar parameters studying the stars by themselves. So, properties of the faint central star are usually analyzed through nebular characteristics. In planetary nebulae, the alpha elements like oxygen, neon, argon, sulfur are supposedly unchanged by the stellar nucleosynthesis, while helium, nitrogen, and carbon can provide information of the nucleosynthesis of these elements. as these elements are produced in the stars and brought to the surface during the different recharge events. Initial final mass relation, which is a fundamental parameter in stellar physics, can be found by nebular analysis, measuring the masses of central stars in a luminosity effective temperature diagram provides masses for pre-white dwarfs, and comparison with evolution models provides the initial mass. For instance, here I'm presenting Hertzsprung-Russell diagrams from models by Miller-Bertolami 2016 of helium burning post-AGB sequences for different masses and metallicities. We have here these diagrams with metallicity of 0.02, 0.01, 0.001, 0.0001. Let's see this one. Above to the left with metallicity 0.02. Here we have the behavior of the central star in this HR diagram, and stars with different masses are shown. If we can determine the luminosity and the effective temperature of the central star by means of, for instance, modeling the planetary nebulae, we can locate this star in this diagram and then determine its mass. And by using the models, we can determine the initial mass of this star. This is one of the very important effects of analyzing these interesting diagrams. I'm sorry I have no time for stay in this diagram more time. I'm going to present a work that we performed some years ago, Hernandez Martinez et al., 2011, where we used planetary nebulae as constraints for galactic chemical evolution models in the case of the regular galaxy NGC 6822. Here we measured the elements of planetary nebulae and H2 regions. H2 regions are presented by this big dot, this big dot. And planetary nebulae, we have two values here for all planetary low metallicity objects and planetaries young that are similar in chemistry to the H2 regions. We have the oxygen, the argon, carbon over oxygen, nitrogen over oxygen, neon over oxygen, sulfur, chlorine, and iron over oxygen. And we are presenting here a model of chemical evolution of the galaxy where the abundances evolve with time. The models were tailored to match oxygen in H2 regions, and models are based on lambda cool dark matter cosmology and the star formation history increasing and bursting. What we found here is that the model presents good predictions for most elements except the case of carbon and nitrogen. The following chemical history arises for this galaxy. Important gas mass loss in the first 5 gigayears. B, no star more massive than 40 solar masses was formed. And C, 0.5 of all 3 to 15 solar masses stars became binary system progenitors of supernova type 1a. We perform this same type of evolution, chemical evolution models for other galaxies that I don't have time to show here. Another work that we performed 2 years ago, Garcia Rojas et al. 2016, is to show that the chemistry of planetary nebulae helps to test AGB nucleosynthesis and AGB stellar evolution models. In this view graph, we present the behavior of nitrogen to oxygen versus helium in the left one, and nitrogen to oxygen versus oxygen in the right one. And we are showing the H2 regions, the abundances of H2 regions in NGC 6822, the same galaxy as before. And these are the red dots. And in black, we have the behavior of planetary nebulae. And we have added to these graphs the behavior of stellar evolution models by Caracas 2010 and Fishlock et al. 2014. These are the lines here. These models were computed at different metallicities. The magenta, for instance, here is the metallicity of 0.004, and the others are lower metallicity. The numbers in these models are the initial masses of the stars. What we see here is that compared to H2 regions, planetary nebulae are helium and nitrogen rich, which is an unexpected thing, because central stars are providing helium and nitrogen to the interstellar medium due to the first and second dredge-ups during the AGB phase. We can see that extreme nitrogen enrichment occurs for stars with initial masses larger than 3 solar masses, in this point, for instance. The models present the surface stellar abundances at the end of the AGB, and we are comparing these abundances directly with planetary nebulae. We can see here is that models, for instance, do not predict the helium enrichment in planetary nebulae. And in other graph that I'm not showing here, we detected that these models does not predict either the nitrogen or the neon abundance in this object. An interesting thing in this diagram is, for instance, that the H2 regions in red are all in the same zone of abundance, nitrogen to oxygen and helium, or in this case, nitrogen to oxygen versus oxygen. That indicates that this galaxy, an irregular galaxy, is an homogeneous, chemically homogeneous galaxy, while the planetary nebulae present very diverse abundances. I'm going to change to these galaxies. Since long ago, it is known that these galaxies present chemical inhomogeneities. Many authors, works by many authors, based on the chemistry of H2 regions, shown that a negative chemical gradient exists. A negative chemical gradient exists in the disk of most spirals. The chemical abundance of oxygen, nitrogen, carbon, and so on decrease with the galactocentric distance. Low heavy element abundances are found at larger galactocentric distances. This has been interpreted as a result of the chemical evolution in the galaxies. We decided to calculate this gradient using planetary nebulae. Why is that? Because it is crucial to know if gradients evolve with time. Does the gradient become flatter or steepen with time? Is a question already not answered. This can be studied by analyzing the gradient with objects of different ages. And being planetary nebulae objects of some gigayears old, they could provide information about the evolution of gradient in the disk. It has been found that planetary gradients are flatter in most of the studied galaxies. Here I'm presenting the case of the Milky Way, where chemical gradients of planetary nebulae are compared with chemical gradients of H2 regions for oxygen, neon, and argon. In red, in this diagram, it is the gradient of H2 regions, and the black dots are the planetary nebulae. We see that PN gradients for oxygen, for neon, for argon are flatter than the gradients of H2 regions. Besides, at the distance of the sun to the galactic center, about this distance, more or less, or oxygen and neon abundances are larger in planetary nebulae, which is very strange. Argon, on the other side, the abundance of argon in planetary nebulae are the same for H2 regions, are the same as in H2 regions. But keep in mind that data are predicting larger, flatter gradients in planetary nebulae than in H2 regions. Here I'm showing the case of the galaxies M31 Andromeda and NGC 300. The case of Andromeda is very interesting. In red, again, we have the gradient of H2 regions as derived from data by Zurita and Bresolin in 2012, while the planetary nebulae in black show this very, very flat diagram, very dispersed also. The same is occurring in NGC 300, where in black the planetary nebulae are shown a flatter diagram than the H2 regions in red. So in both galaxies, PN gradients are flatter than H2 gradients. M31 is an extreme case. PN gradient is 0 up to distance larger than 100 kiloparsec, showing that PN abundances are independent of galactocentric distance. And what can be causing this? Migration of planetary nebulae in the disk, interactions or mergings with other galaxies are also probably causes. Discussion and conclusions. I have presented some interesting results obtained on planetary nebulae. PNE have been used by us to constrain chemical evolution models of a couple of regular galaxies. Here I presented the case of NGC 6822, where the population of planetary nebulae, old and young planetary nebulae, analyzed by us helped to derive an evolution model for this galaxy. Second, PN have been used to compare their chemistry with the prediction of stellar evolution models of LIMS, or for AGBs. We found that models do not reproduce helium or nor neon abundances in planetary nebulae. We use planetary nebulae in the Milky Way, M31 and NGC 300, to analyze their chemical gradients in comparison with the gradients found from H2 regions. It is found that planetary nebulae gradients are always flatter. The most extreme case is M31, where the gradients from planetary nebulae is 0, showing that PN abundances are independent of the distance to the center of the galaxy. All the planetaries in M31 present more or less the same chemical composition, independent of their positions in the galaxy. Migration, interactions, and mergings with other galaxies are possible causes for this peculiar behavior. And that's it. Gracias por su atención.